this is working. All right, excellent. And maybe I use this guy. Or no? Are the slides there? Up there, yeah. So yeah, actually, there was maybe some mix-up in my email account. So I thought the title is My Quantum Journey or Your Quantum Journey, but then last night I learned it's Quantum Computing for Good, and this is why I changed it. So I just included there My Good Quantum Journey, which is a superposition now of the two titles. So we are very quantum here as well. And as you mentioned, yes, I had the honor actually. This, what you see there is a picture of me here in the Deutsches Museum in some other place talking 2019, and this was actually the very first public speech I gave on behalf of IQM. And if you look closely on the title back then, Shaping the Quantum Future from Europe, I think this is still very much to our heart of what we do. And also later today, we will maybe get a little bit more feeling on what was maybe the intention between this phrase there, can quantum technology empower humanity? So I learned only when I created these slides that we had already this idea back then, which of course is very, very important, how we use the technology for the good. So I will talk a little bit about quantum and the journey, and since we are in the Deutsches Museum, a little bit about history as well. And I try to include there where I was always at these stages when important things happened. So when we talk about quantum, I think one of the first persons was this guy here, Max Planck, in 1900, where he proposed the hypothesis that energy is quantized and radiation is quantized. And this is very much one of the resources that we use also in quantum computing, of course, that we have certain packages of energy and so on. And in 1900, of course, I wasn't really there, so my age was minus 85 years roundabout, and maybe I was watching from somewhere outer space, or I don't know how it works, but anyways, I think it's very important discovery back then. And since then, quantum physics has been discussed between scientists, and at some point first experiments have been made. And the second person also I wanted to mention here is this guy, Richard Feynman, who brought up maybe the initial idea of a quantum computer. And I like this picture because what we do here at the festival is kind of celebrating technology and combining it with arts. And Richard Feynman, I mean, I didn't know him, but what you can read about him is that he was kind of a person who liked to live as well. And you see him here playing the drums. So this is what people say, that he was enjoying this lifestyle as well. And I think this is something that we also celebrate here, is how can we combine deep tech, technology, science, maybe sometimes with arts or other topics as well. So he was maybe a visionary for the festival that we are having here today. And he said this famous sentence that many of you may have already seen, maybe, that where he said, nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. So he didn't use the word quantum computer back then, but this is the concept that we use in the quantum computers, that we use a quantum mechanical system to solve problems which somehow map nicely into quantum physics. It doesn't have to be, let's say, a molecule also, which anyways follows quantum physics, but it just needs to map nicely onto the laws of quantum physics. Is this working? Maybe. Yeah. So 1981, I was already getting closer, coming from outer space, so I was only minus 4 years old, so almost there. And then I did a little bit of research, actually, what happens in terms of quantum computing, and why it is happening, and just a small recap for those who are not so familiar. So why is there actually this hype about quantum computing? Why is it so powerful? And I think the idea that I just mentioned, that you can map certain problems onto a quantum system, this can be applied for all kinds of problems, and you see here a landscape, and you see many of them are actually very science-driven or R&D driven, and if you look into the use cases that are currently being discussed, many of them are in the area of chemistry simulations or drug discovery or so, which we find there. But actually, it can go all the way, maybe also even to finance, which is maybe not so intuitive, right? Why would a finance problem map onto a quantum computer? And this, of course, this is then more to the mathematical structure of these problems. But the idea is that there is a class of problems which is so complex that with the most powerful computers, we will never be able to solve them. And this is the big promise of quantum computing. So in a sense, there are two kinds of problems where quantum computing could help. The first problem type is where it just creates a little speed up. So if you take the finance example, and if you are a bank and you want to price some options or something like this, you might be already happy if you're just a little bit faster than the competition and you get the gain out of it. So this is just being a little bit faster, but this is also something that we can try tackle with classical computers. We just build more and more powerful systems. The other part of the problems is those which we never even start computing, because we already know it will take thousands or millions of years if we do it in the exact way. And I think this is really the interesting part, and this is one big reason why there's such a big interest in quantum computing. And there are a few examples out there that you kind of continuously read when you read articles about quantum computing. And one of these examples, a simulation of larger molecules, where if you would like to do such a simulation and if you want to save the computational states in between, you will need to have a larger memory than we have atoms in the universe. So even if we tried, there's no way to do this. And I think these are the kind of problems that ultimately are the motivation to build the quantum computers. And then, of course, also, if we are talking about quantum computing for the good and what can we do, I think one very important topic is the sustainability and environmental aspect. And, of course, there are always two points to the topic. One is how much energy is consumed in total by the machines that do the calculations. And big computing centers, they do consume quite a lot of energy. But then the other, maybe even more powerful one, is the use cases that you enable. So if you think, for example, about the development of new material, right, if you would be able to find a material to replace cement or concrete, what we use to build our buildings, this is a significant fraction of the CO2 emissions comes from this industry. So if we would have an alternative there, we would actually be able to reduce strongly the CO2 emissions. And I think this is the power. So not that the quantum computers itself might use less energy, but the use cases that we enable on those systems. And they can come from a broad variety. So you see here, and if you just look, you might find examples for many of these fields where a quantum computer enables a use case that help us reducing CO2 emissions. And I think this is really an important problem that we as a society as a whole need to work on. So what happened after 1981? In 1985, this guy, David Deutsch, he was working on a principle on whether it's possible to build a universal computer based on quantum physics, and he wrote this paper here about a certain theory that proves that it's actually possible. And I think he was kind of thinking very hard about how this works, and you see from his gesture. And actually 1985 was the year then when I finally arrived on this planet. And if you look at me, maybe I have a little bit less hair, but I still try to imitate this gesture. So maybe I was already thinking about how to build the quantum computer of the future. So this was 1985, still a very scientific topic, of course, and still very conceptual and theoretically, but nevertheless a very important milestone back then. And then a big breakthrough, I think, when it came to the really commercializing and pushing the technology was 1994, when a guy named Peter Shaw was developing this algorithm which can be used to factorize large numbers, which might sound very mathematical, and you think about, okay, what is this? Why would I be interested in factorizing large numbers? It's a math problem in the end. But then if you look closely on where such kind of problems are used, you actually find out that in many encryption algorithms that we use, for example, this RSA encryption, this is used. And this was the reason why since then actually a lot of governmental institutions started funding this topic quite heavily, because this in the end might be an opportunity, but might also be a threat if you're able to run such calculations. And 1994, I was more still in exploratory phase, kind of watching for things to happen, not really contributing, of course, to the topic. But just to give you an example on where, kind of how powerful this could be if we had a large-scale quantum computer, I just bring here an example. This is not calculated by us, but by others, and they estimate roughly the time scales. So this assumes that we would have really a very large-scale quantum computer, millions of qubits error-corrected. But nevertheless, it gives you this kind of idea where we say, okay, we can bring problems from not very human timescales, because no one wants to wait so long, to a timescales in seconds. And of course, it's still a long way until we might have such a machine, if ever. But nevertheless, this was the reason why since the 90s, especially in the US, a lot of funding has been pushed into the field and also to develop such machines. So until then, it was more like a theoretical idea. So people have been talking about, okay, can we build such machines? What are the fundamental kind of requirements that we need? But since then, since the mid-90s, maybe people have really thought about how can we build such a machine from a kind of physical point of view. And of course, since then also we have this debate, is quantum computing a threat if you kind of crack error correction, and if then you use the technology to maybe decrypt information that others don't want to share necessarily. So I said, since the 90s, people tried to build these machines, and here you see two pioneers from Yale universities, how they are working on a machine in the 90s, and it looks very experimental. But if you look closely, and if you Google quantum computing, you actually see that at least for the superconducting systems, the structure still looks very much the same. Maybe a little bit cleaner now, a little bit more organized, but in the end, you have these horizontal golden plates there, which are just different temperature stages. So the whole concept of quantum computing with superconducting circuits is based on the fact that we build a processor that operates at very low temperatures. And at these low temperatures, all the background noise is so low that it doesn't disturb anymore the quantum effects, and we are able to observe them on the one hand, but then also manipulate them. And this manipulation is exactly how we encode, in the end, the algorithms there. So a lot of academic research has happened in these early 2000s, in the US, also in Europe, leading universities in Japan. I think the first superconducting qubit, is it there? Yeah, is from Japan, NEC, and they were really leading back then also on the technology side, but it was mainly academic, so it was really an academic effort trying to build systems where you somehow could encode a problem in and you get an answer back after some time. During this time, I was also not so much into science. I was more focusing on sports, so I was very competitive in rowing and basically spent all my time in the boat on the water. But nevertheless, more important people have actually contributed quite heavily to the field back then. And then 2011, at least for me, was another important year. And there, at least it was an interesting experiment, actually, from the group at UCSB, which later became the Google team. So what Google did, I think, in 2014 or 15 or so, they kind of attracted the whole Google team to become the Google hardware team. And they did a very interesting experiment which combines somehow the ideas of superconducting quantum computers with the disadvantages that we have. So the disadvantage for these superconducting technologies that we use is that there are a lot of loss mechanisms and we are losing energy. And sometimes actually we are losing energy into other microscopic systems which are embedded in the wafer. So this can be if there's an atom missing, for example. So you have a silicon grid and at some point there is an atom missing, this starts resonating and you can lose energy. But what they actually showed is in this nice experiment that they can lose energy into this quantum system and then it comes back. So they called it back then a quantum memory, which still is something that, at least to my knowledge, doesn't really exist. So what we have nowadays are so-called quantum processors. So these are units that just process information. But if you look at your normal computer, usually you have a memory, right? You can store your documents or whatever. And this is, of course, it would be great to have also on the quantum side, and many scientists are working on this, but still it hasn't really been the case that we have a computer in a sense where we have a processor plus a memory and we can somehow store quantum information in the memory and then at some point take it back. But nevertheless, this was, I think, a nice experiment that went into this direction, which also got a lot of attention back then, and I picked this year 2011 because this is when I started my PhD here in Munich at the lab at the Walter Meissner Institute for Low Temperature Physics. So you see me there in front of the cryostat that I was using and building. You see also a dog lying around there, so I have a strong affinity to dogs. This dog was back then visiting the lab, and I was lucky enough then after a few years actually to finish my PhD in 2016. And if you look at my PhD hat, actually you see that someone put there also some dog food thing, because actually many years during my PhD I had a dog sleeping under my office. A lot of quantum physics is about cats being dead and alive. I had a dog which was mostly dead, kind of sleeping under the table, and then sometimes got to life. But anyways, that's a different story. So this was 2011, still very kind of scientific. So you see even this UCSB group was not yet in Google. I was doing basic research on quantum physics, quantum topics. And then it took basically until 2019 until this announcement came out. So meanwhile, Google has attracted the UCSB team, and they were running experiments on larger and larger quantum processors. And the idea is that unlike a classical processor where the computing power more or less scales linear with the processor size, so this means that when you want to compute twice as fast, you need kind of twice as big processor or twice as many. In quantum, this goes more towards exponential scaling. And so Google has been working on different processors, 9 qubits and then increasingly. And then at some point they got into this regime where they did an experiment with, I think, 53 qubits at this time, where they were running an algorithm on this processor, and they estimated that this algorithm would take a few thousand years on the most powerful computer. I think a few days later, IBM came with a press release and said it only takes a few days, but I think nevertheless the story is they did this in a few seconds. So this was the first time where people claimed that they have run an algorithm on a quantum machine that was outperforming a classical computer. The thing is, and one has to be quite careful with this, that the algorithm they were running, it didn't have a lot of usefulness. So it was more or less a random circuit that they were executing, which is very hard to simulate for classical computers. But nevertheless, it was a great achievement. And 2019, actually, this also gave us a great push, because this was the year when we started IQM. So we kind of started riding on this wave, and of course this helped us a lot. So this is actually some pictures from the opening ceremony for IQM. And you see we were building up there a stage to make some announcements. And it looked quite different maybe from what we do today, but nevertheless it was a lot of fun. And also if you look at, you don't really see it very well, but this is actually a picture taken from our office, the first office, and you see in the background there's actually a system, a quantum computer standing in the office. So the first, because we wanted to act as fast as we can, we just kind of got the system into our office. We drilled a hole into the floor and put the cooling machine into the parking lot downstairs, and then was operating it like this. So it was really kind of startup style. Not a garage, but I think it comes very close to a garage. And of course, since then, times have changed, and many things have changed for us in the ecosystem. Many more companies have emerged and become more and more mature, and we were kind of part of this journey and have evolved as well. So if you look at the stage, it evolved from this point into a stage. So this is a company event we had last year, and this is the IQM band. So we have a very professional band playing songs, and you look also, the stage looks a little bit more professional than what we have there. And of course also our technology has evolved since then. So instead of having the systems in our office, we meanwhile actually, and I cannot show photographs because there are some security reasons for this, but we have around 8 systems. In Finland, we are now operating on 20 qubit processors ourselves with, for the expert at least, quite nice 2 qubit gate fidelity. So this is how we have developed as a company. And something to mention, coming back again to this quantum computing for good, is also at some point we have developed our mission statement. The creation of this mission statement was so that we have sat together with our employees and really discussed, okay, why do you think you work for IQM? What is the journey, and what is really driving you? And we realized that actually many of our employees are very purpose-driven. And we always had the slogan as a company, we build quantum computers, which is very short and crisp. But then actually, if you look at the mission statement, you see this part of the sentence, that we build quantum computers, obviously, but we do it with a certain purpose. And the purpose is for the well-being of humankind. This, of course, it sounds quite vague, and you might ask what it means, and I will come later with some example on what it means, but this really shows a little bit the spirit that we have, the DNA of the company, that we want to use the technology to do something good, and we want to do this now, even though the quantum computers don't yet outperform the classical ones, but then, of course, also in the future. So 2019 was another thing happened, and of course I didn't plan this, but Finland took over the EU presidency, and being a Finnish startup, actually a lot of pleasant surprises came up with this, because what they do in such a case, actually they organize most of the events in Brussels that are there, these kind of road tables with all the 27 member states, and they also organize quite a lot of events then, for example now in this case in Helsinki, in the capital. And this led to the fact that quite early on, we actually got very well connected to certain decision makers, also in the field of policy, and we were really trying to push this European story. So if you look at IQM, we really want here to set an example on how you can build great technology out of Europe and how to make a global leader out of Europe. And of course, this is something you cannot really plan, but this was kind of the kickstart, and getting this strong support from Finland, which then at some point also, of course, was extended to other countries. So you see me there with the previous German Minister for Research and Education, or with a French president. So I think this European feeling is something that we have, and I think something that we utilize and should utilize also as a society. And we try to be very active in this and really build European leaders. Not only IQM, I also personally try to support many other startups as much as I can in going this journey and growing on this path. So IQM, for those of you who don't know so much, we are meanwhile a company which has more than 180 employees. We have a lot of fun when we work or when we party together. We are working in 4 different locations at the moment. Our headquarters are in Espoo. So this is actually a picture from our office building, nicely located there at the sea, close to Helsinki. We have close to 50 employees here in Munich. And we are starting now in Madrid and Paris, where we have a handful altogether. So this is kind of how we see ourselves. And what we do as a company is that we build quantum computers, these systems. I will explain this in a little bit more detail. And then we sell them out. And we really see ourselves here as a full stack company developing all the necessary technology. And as said, this is something that from a European perspective is seen as a very strategic topic. And for example, we have recently announced that we get a lot of support now also from the European Investment Bank. And actually the president, Werner Hoyer, he came personally to Finland to hand over these documents. So this nicely shows how important the Commission and these organizations actually see these topics. So what do we do as a company? What is the technology? What's the innovation we are driving? Similar to a normal computer, we are building the hardware for it, and the heart of the quantum computer is the processor. And this is very analog to what you see in semiconductor chip industry. So first of all, you have to make a design of the processors. And in semiconductor industry, you have leading companies like Cadence or Synopsys or so. However, these simulation tools, they don't really work for the quantum processors because it's different physics. The underlying physics is different. So we have actually put a lot of effort in developing our own software tools to first create the layouts for the processors and then do the simulations. So actually quite a lot of IP is created here in this first step. And we simulate so that we can anticipate the performance of the processor. And once we have good simulations, we do the tape out, which means we start producing on a wafer scale. So the base wafer, kind of the substrate, is silicon, as in normal chip industry as well. And we start processing on a 200 millimeter kind of wafer scale. We have our own production facility. So we have invested meanwhile more than 20 million euros into our own fab clean room to produce these chips. This is of course also again coming to this European topic. It's part of this chip shortage, European Chips Act. How can we ensure that for the most important technologies we have the capacity in Europe to build it? So we work on 200 millimeter wafers, and then we cut them down into pieces like this. So this is one of our processors. It's actually 2 silicon chips flipped on top of each other that you see here. This is the so-called flip chip technology, and the control lines. This enables us to bring control lines from the top and from the bottom, so we can actually nicely control all the qubits in between. And then we build a complete system around it, and we don't produce all the components for the system, so we see ourselves more there as a system integrator. So we buy a lot of electronics, classical control electronics, cables, other things. So this is kind of what we do. And why actually do we do all of this ourselves? Well, one reason is that it doesn't exist. There's no commercial alternative really to do this that we could just take. But then also in the end it's all about speed. So we are competing with the biggest companies like IBM, Google and others. So we need to be be as fast as possible. So the idea by covering this complete value chain is that we can accelerate the R&D cycle as much as we can, and in this way build better and better processor faster and faster. And then on the kind of vertical integration, we don't develop ourselves the full software stack, but we integrate into existing frameworks. So for the experts, there are a few programming frameworks like Qiskit from IBM, Circ from Google, or QLM from others. So we build adapters to those, and then people who know how to use these programming tools, they can actually access our machines and then make use of them in the end. So yeah, this is in the end how it looks. We build the complete quantum computers, and the business model, I said, is to sell them out, for example, to big data centers. So this is still a rendering, and we have a few cases where we are doing this. One in Finland with the State Research Center VTT, one here in Munich, or in Garching to be more precise, with our friends from the LRZ, the Leibniz Rechenzentrum. They get such a system, and this is the idea to enable, in this sense, science, education, and also enable early adopters to get used to the technology. I will skip actually the video because I've been talking too much, but if you are interested, just check out our YouTube page and you will find there the nice video. I still have a few slides left coming to this quantum computing for good topic and how do we want to use the technology. So these supercomputing centers where we kind of target to sell into, they are work on some of the most important topics that we need to solve, like drug discovery we have seen during the pandemic, of course, and also climate change. And they really want to get into quantum computing because they need to scale their computing power. They are under an innovation dilemma, so they need to get more and more computing power, yet they have these restrictions maybe on energy consumption, size, and also price of the systems. So this is the idea why they are interested, and as said, we have two of these examples. One we delivered in Finland, which was kind of investigated by Ursula von der Leyen up there, and now the newest one will go here in Garching to the LRZ, and also we had the Bavarian Minister for Research and Science visiting there recently for the 60 years anniversary party. This is kind of what we do. We bring the technology to the computing center so they can start working on this. Coming to the use cases, so this is something where I started with, how can we use the technology for the good? So we did an analysis on what are the possible use cases and might there be an impact on climate. And we looked at two cases. One is actually the energy storage problem, and the other one, oops. No, it's black. The other one is an energy grid optimization problem. And we found out that with both of these use cases, actually, it's possible to save more than 100 megatons of CO2 per year, which by the year 2040. So we're not saying that this will happen tomorrow, but by the year 2040. So this is kind of what we did. And we didn't do this alone, but actually we did this with an investor called World Fund. And throughout this assessment, actually, we got to know each other better and better. And this is then also the reason why today we announced that World Fund was leading our very recent funding round, 128 million round, which we are using to develop the technology further, develop such kind of use cases on our system. So we are very happy to have World Fund, many other investors also joining the round, so a very strong consortium. Thanks to all of them. We are celebrating this usually in the company. We have a so-called gong, and whenever something great happens, someone is hitting the gong so that really everyone understands that now something significant has happened. So yay, we are happy to have closed this round. We announced it today. And yeah, thank you to all of you for being here, listening to me. Whoever has supported us in the past, a big thank you. Everyone who has worked with us or for IQM. I think this was really a team achievement, and big thanks to everyone. And I think I went a little bit over time, but nevertheless.
No. Well, we don't have time for Q&A. Thanks, Jan, for this fascinating keynote. Congratulations.